Hello there and welcome back to this video series on control systems. We have seen in the previous class how the dynamic equations for each section of an armature controlled DC servo motor can be written, and a few quantities such as time constant of the motor, the stalling torque, the no load speed, the rated speed, and the rated torque can be derived. We have seen that this rated speed and rated torque refer to the steady state speed and steady state torque such that the motor develops maximum power. In this class, we will show a problem which shows how experimental results can be used to predict the performance of the motor under certain loading conditions, or how to calculate certain important motor parameters from these experimental results. The problem we are considering is shown over here. It refers to a armature controlled DC servo motor which is supplied with voltage 50 volts ESEA and is running at 1800 RPM. When it says this, it is steady state speed and develops a power, steady state power of 2 kilowatts. Motor inertia is this much. Motor viscous coefficient is this much. Load inertia is this much. Load viscous coefficient is shown over here. In addition, there is a speed reduction uh, gearbox between the motor shaft and the load shaft. We'll see how to incorporate this also. There is a little consideration that you can remember. Given all these, you have to find the time constant of the motor and also what happens when an additional load 2 Newton meter is applied on the motor shaft. From this problem, we'll start with the torque speed characteristic graph. I would encourage you to remember this very carefully. You have stalling torque here, you have no load speed here. The maximum power point is at the midway between this A and B on the line, torque speed line. This is stalling torque divided by 2, no load speed divided by 2. When once we remember this graph, we will try to look at the data given in the problem and try to identify various numerical values. By noting that the torque speed characteristic or the equation of this line comes out to be something like this, and we notice that the rated speed is 1800 rpm in radians per second. 2 pi n by 60 comes out to be this, and we know the rated power is 2000 watts, that is T rated multiplied by omega rated is 2000. So you find what is the rated torque as power by speed as shown over here. So we know what is the stalling torque. Stalling torque is twice the rated speed. No load speed, stalling torque is twice the rated torque. No load speed is twice the rated speed. So we find these quantities. So at point A, you have 21 Newton meters of torque, and at point B, you have speed as 120 pi radians per second. These numerical values are shown over here. The coordinates of point A are speed is equal to 0, torque is 21.2 Newton meters. At point B, the speed is 120 pi and the torque is 0. With this, we try to note that at point A, torque is 21.2, from which we see K1 as 0.4024. We recall that K1 has an expression Km by Ra for it. Similarly, we notice at point B, torque is 0, speed is this much. So you substitute both into the torque speed equation to get the value of K2. Remember that K2 is Km square by Ra. So if you divide K2 by K1, you have Ra get cancelled, you get Km. Essentially, that's what we are doing. K2 by K1, which is motor constant, is 0.14 Newton meter per ampere. Remember the units. Once Km is known and we know the value of K1, Ra can be found. So this Ra is found to be 0.35 ohm. Computation so far, K1 is computed, then K2 is computed. From K1 and K2, motor constant Km is computed, and from which motor resistance Ra is computed. Next we compute further quantities that we need. One quantity that we need is J equivalent, which can be given as motor inertia plus 1 over gear ratio square into load inertia. How to derive this, we'll see at some point of time, but just remember when you are given that there is a gear train between motor shaft and the load shaft, you find the equivalent inertia as shown over here. So Jm plus 1 by gr square Jl. Similarly, the net equivalent inertia is found as shown here. Once you have all these quantities in place, you say tau m is zero point 0.2 seconds. Tau m is equal to 0.2 is answer to one part of the question. For solving the other part about the steady state speed when an additional torque is applied, we'll come back and look at the equation given here. Km into EMSS minus this divided by whatever is this quantity here. We take a differential on both sides, that is delta is applied on both sides. So delta MSS, which is new speed minus old speed, is written as Km into delta operating on ESS minus Ra into delta operating on TD. Okay, we know omega old is the speed before additional torque is applied. Omega new is the speed after the additional torque is applied. Since the voltage did not change at all, we note that this quantity delta ESS is equal to 0. Delta TD is 2 Newton meters, that is the old torque minus new torque is 2 Newton meter. We substitute these values to get omega new minus omega old is equal to so and so, Km into 0 minus all these quantities, from which we see omega new is omega old. Omega old is 60 pi minus 3.6. So in summary, we saw a problem where a real life situation, that is a motor which is subjected to a disturbing torque, a real life situation, how experimental results, that is the steady state speed, steady state torque, can be obtained by experimental results. How these results can be used to contribute certain important system parameters such as Km, K1, K2, armature resistance, and so on, and also to predict the system behavior. That's all we have for now. Have a great day.